Hello everyone and welcome back to my channel. I am Sahil Sawant and I am currently pursuing MTech in Computer Engineering at VJTI Mumbai with some background in Electronics and Telecommunication Engineering and research experience in RF systems and radio astronomy. So far in this series, we have observed in episode 1 we discussed how signals carry information. In second episode, we discussed how Fourier reveals frequency structure. In the third episode, we moved on to sampling, which must follow the Nyquist rule. In the fourth episode, we discovered how spectral leakage distorts our analysis. In the fifth video, we looked at how noise limits the performance of the signal. In the sixth video, we saw how FIRs are different from IIRs and how there is an engineering trade-off between both of them. In the seventh episode, we saw how convolution defines system's response. In the eighth episode, we discussed how spectrogram shows frequency evolution over the period of time. And now, today, we are going into a little bit of deeper question. Even with spectrograms, is Fourier always enough? The answer is going to be no. And that is why wavelets exist. Fourier transform assumes something most fundamental. It uses sine and cosine waves that extend up to infinity. Even in spectrogram, we still use fixed size windows. But real signals often contain sudden spikes or they might even contain short-lived bursts. They also contain sharp transitions and some discontinuities. These are localized in time domain. Sine waves are not localized and they extend forever. That's the mismatch. Now, in spectrogram, we used fixed windows. That is, short windows means good time resolution. That means poor frequency resolution. And longer the video means good frequency resolution but poor time resolution. But what if your signal contains slow oscillations but for longer duration of time or some sudden spikes lasting just a few milliseconds? One window size cannot optimally capture both of them. What we need is something much more adaptive. Wavelets solve this thing by using short waveforms that are localized in time domain. Unlike sine waves, wavelets are finite, compact, and localized. Wavelets are small oscillatory waveforms that can be stretched and shifted. Instead of analyzing signal with infinite sine waves, we analyze it with scaled and shifted wavelets. This allows for multi-resolution analysis. Now here is a key idea. Wavelets use small wavelets to detect high frequency and short events. Large wavelets are used to detect low frequency and long events. This automatically adapts to the resolution. High frequencies get good resolution. Low frequency get good frequency resolution. This matches how the real signals behave, and this is called multi-resolution analysis. Imagine a signal that has slow oscillation but suddenly has sharp spike. Then it returns to smooth behavior. Now fast Fourier transform, that is FFT, gives us the frequency content. Spectrogram gives us the time and frequency heat map. Wavelet transforms these highlights into the exact location of the spike, its scale and its intensity. With sharper localization, and wavelets zoom into the transients as well. There are two main forms. The first one being continuous wavelet transform, which is represented by CWT. It provides detailed time scale representation and it is used for analysis and visualization. The second form is discrete wavelet transform, that is represented by DWT. It is used for signal compression and it is used in denoising as well. It is also has its fundamentals in feature extractions. Let's say for example, there is JPEG 2000 which uses wavelets for image compressions. Biomedical signal denoising uses wavelets extensively. Now let us look at its application in engineering as well. Wavelets are powerful in EEG and ECG signal analysis. They are used to detect abnormal spikes. In astronomy, we use it to represent or to capture transient burst detection. Fault detection in power systems is also identified by sudden disturbances in the signals. In image compression, efficient multi-scale representation. And in structural vibrational monitoring, we use it for identifying localized damage. Whenever signal have sudden changes, wavelets are the things that shine the most. Now let us compare Fourier, spectrogram and wavelet. Let us summarize it clearly. Fourier is global frequency information. It has no time localization. Spectrogram, on other hand, has fixed time and frequency trade-off. It uses a sliding window. Now, looking at wavelet, it has adaptive multi-resolution and it has better transients detection. Fourier sees the structure, whereas spectrogram sees the evolution. And wavelets do not replace Fourier, they complement it. Fourier is still powerful for stationary signals. Wavelets are powerful for non-stationary signals. Engineering is not about choosing the right tool, not replacing everything. Engineering, on the other hand, is finding the right tool for the right problem or giving a right solution. If you remember one thing today, let it be that when signal changes suddenly, sine waves are not the best language to define it. Wavelets speak the language of transients. Signal processing evolves because signals evolve on their own. In the next episode, we move on from theory to reality. We are using software-defined radio to capture real radio frequency signals because everything we have discussed so far comes alive when we observe the real world data. Welcome back again to Signals and Stars. Hello everyone and